FCS in Ethernet. The frame check sequence, FCS, is a critical error detection mechanism located at the end of every Ethernet frame. It is designed to ensure the integrity of the data transmitted across the physical medium. Purpose: the primary purpose of the FCS is error detection, not error recovery. When data is transmitted over a network medium, it is susceptible to errors caused by interference, noise, or physical damage to cables. The FCS allows the receiving device to determine if the frame has been corrupted during transmission. Mechanism: cyclic redundancy check, CRC32. The FCS mechanism relies on a powerful mathematical algorithm called the cyclic redundancy check, CRC, specifically CRC32 for Ethernet. The process works in two stages: one at the sender. The sending device, example a computer, switchport, or router, treats the entire content of the frame, from the destination MAC address to the end of the data payload, as a single binary number or a polynomial. It performs a complex mathematical calculation, CRC32, on this data. The result of this calculation is a 32-bit, 4-byte, checksum value, which is placed in the FCS field at the trailer of the frame. 2. At the receiver. The receiving device performs the exact same CRC32 calculation on the received frame data, excluding the FCS field itself. It then compares the result of its calculation with the FCS value included in the received frame. If the calculated FCS matches the received FCS, the frame is assumed to be error-free and is accepted for processing by higher layer protocols. If the values do not match, the receiver assumes the frame is corrupted and silently discards it. Handling errors. Ethernet itself, operating at the data link layer, does not have a built-in mechanism for error recovery, retransmission requests. It simply discards bad frames. It is the responsibility of higher layer protocols, such as the Transmission Control Protocol, TCP, at the transport layer, to detect the absence of the expected data and initiate a retransmission process if reliable delivery is required. The Ethernet CRC32 mechanism uses a specific mathematical expression known as the generator polynomial, which is defined by the IEEE 802.3 standard. This polynomial dictates the precise binary division operation performed on the data frame. The IEEE 802.3 CRC32 polynomial, the standard generator polynomial G, X, for Ethernet, also used in numerous other applications like PKZip and PNG files, is representation and implementation details polynomial form. In the equation above, each x(n) term corresponds to a bit position in the binary representation, where the coefficient is 1. The highest term, x(32), signifies a 33-bit divisor. Hexadecimal representation: in hardware and software implementations, the most significant bit, MSB, the x(32) term, is often implicit and not written, as it is always a 1 in the divisor. The polynomial is typically represented in hexadecimal as 0x04C11dB7. The 1 bit for x(0) is on the far right. Reflected form, 0xEDB88320. Due to historical reasons related to how the first Ethernet hardware transmitted data, least significant bit first within each byte, the standard algorithm involves a process called reflection or bit reversal during the calculation. Many software implementations use a reversed polynomial constant, 0xEDB88320, along with specific initial values and final XOR steps to achieve the same result as the hardware-oriented IEEE 802.3 specification. Modulo 2 arithmetic: the division process in CRC is performed using modulo 2 arithmetic, binary arithmetic with no carries, which simplifies complex addition and subtraction operations to simple bitwise XOR operations. Error detection capability: the specific design of this polynomial provides robust error detection capabilities. It is guaranteed to detect all single-bit and double-bit errors. It detects all errors involving an odd number of bits. It detects all burst errors, consecutive erroneous bits, of length 32 or less. This carefully selected mathematical property is why the CRC32 remains an effective and widely adopted standard for ensuring data integrity in modern networks. Why CRC32 detects all double-bit errors: the ability of the Ethernet CRC32 code to detect all errors up to 2 bits is a property inherent to the structure of any standard cyclic code with a carefully chosen generator polynomial. The specific properties that guarantee the detection of double-bit errors are: 1. Polynomial length: the generator polynomial G, X, for CRC32 is 33 bits long, x(32) is the highest term. This length is sufficient to detect errors spanning a certain distance within the frame. 2. Specific mathematical properties: the selected polynomial G, X, is constructed such that it is not divisible by x(k plus 1, for any that corresponds to the possible distance between two single-bit errors within the maximum supported Ethernet frame size. 3. Hamming distance: the code effectively imposes a minimum Hamming distance of 3 between any two valid code words in the Ethernet system. A code with a minimum distance of _ can guarantee the detection of all up to d_min1 errors. Since the distance is 3, it guarantees detection of 3 1 equals 2 errors. In short, The mathematical structure of the chosen 33-bit cyclic generator polynomial, as defined by the IEEE 802.3 standard, ensures sufficient mathematical distance between valid data patterns to instantly identify when up to 2 bits have been flipped. In Ethernet, the frame check sequence, FCS, calculation is a complex process typically handled automatically by hardware, the network interface card or NIC, for performance reasons. The process involves treating the frame data as a binary polynomial and performing modulo 2 division using the standard CRC32 generator polynomial, 0x04C11dB7. Here is a simplified, high-level example of how the mechanism works in principle. Scenario A: host A, wants to send a very short, simplified frame payload containing just the hexadecimal value 0x03, binary 00000011. The steps involved. The actual Ethernet standard uses specific bit reversal and initial XOR ring procedures to ensure robustness and hardware efficiency. The example below illustrates the core mathematical idea, polynomial division, rather than a line-by-line hardware simulation, which is highly complex for CRC32. 1. Data preparation. The input data for the CRC calculation includes the destination MAC, source MAC, length/type field, and the data payload itself. For this simple example, we'll use our message 0x03. Message M, binary 11, leading zeros are often handled by initialization constants in real implementations to avoid issues. 2. Appending zeros, the mathematical basis. The algorithm conceptually appends 32 0 bits to the message, creating space for the eventual 32-bit CRC value. Augmented message, 11 followed by 32 zeros. 3. The division, modulo 2 arithmetic. The augmented message is divided by the 33-bit CRC32 generator polynomial g, x, using binary arithmetic with no carries. XOR operations replace subtraction/addition. Divisor g, x. Simplified example. For a much smaller example to illustrate the process, let's use a 4-bit polynomial 10,011, x caret 4 plus x plus 1, on a message 110, 101, 1011. The division yields a quotient, which is discarded, and a remainder. This remainder is the checksum. For post-processing and FCS insertion in the full Ethernet standard, the 32-bit remainder is subjected to a final bitwise XOR operation with the value 0xFFFFFFFF, all ones. The resulting 32-bit value is the frame check sequence, FCS. This 4-byte value is appended to the end of the data frame during transmission. The receiver's role 1. Reception, the receiving NIC receives the entire frame, including the appended FCS. 2. Recalculation, the receiver performs the exact same CRC32 calculation on the received data portion of the frame, excluding the received FCS. 3. Verification, the receiver compares its locally calculated CRC value with the received FCS value in the frame's trailer. 4. Action, if they match, the frame is considered valid and processed. If they do not match, the receiver discards the frame immediately, assuming data corruption occurred during transmission. In practice, a common way to verify a frame is to run the CRC algorithm over the entire received frame, data plus FCS. If the frame is error-free, the resulting CRC calculation yields a specific, non-zero signature constant, 0x2144df1c.